Today we're going to be talking about shear stress and strain. This is another part of this idea of stress that we introduced for the first time in the context of normal stress. As I've mentioned on several occasions, this idea of stress, we're kind of building it up through examples. And so we're going to introduce different kinds of stress, and then in a little while later in the course we'll talk about how this is all kind of one concept. This is just different points of view. So we're going to introduce shear stress today through an example of a bolted connection. So let me draw the geometry of our example here, if I can. So we have this connection here that's going to be bolted to a plate. Okay, still getting used to this tablet thing here that I'm using. Okay, so this is one plate here, and then there's a bolt here that is coming down through the geometry of the connection and keeping this connection tight. So the dimensions here are h and h. Then the thickness of the plate is going to be t. And similar to what we did with normal stress, we're going to go ahead and load this thing up with a force P on both sides. Okay, but notice that here, rather than being just a simple axial bar with a prismatic cross-section, we still have an axial load, but the configuration is different. And so your intuition tells you that if the force P is large enough, this bolt actually will shear. We even use the word shear. It will shear off. And so the stress that develops that kind of causes that to happen, we call shear stress. So if we go ahead and look at just this part of the connection in terms of a free body diagram, so we'll create a free body diagram. It looks something like this. So we'll take the bolt out as a free body. We'll draw the forces that are acting. Right, so we have this distributed force coming from this top part here, and then a distributed force coming here. And likewise, on the other side, we have a distributed force. Okay, now, if we turn these distributed forces into resultant forces, you should get kind of the expected result that the resultant force should have magnitude P, and that these resultant forces, as you can guess, should have magnitude P over 2. Okay, so that's a free body diagram. And now the question is what are the internal forces that develop in this free body diagram, this bolt, right? These are the applied loads, the P over 2 on the top of the bottom, and then the P over here. But unlike before, where we just had a very simple stress state, the stress state that develops, the internal force stress state that develops in this is quite complicated. And to introduce the idea of shear stress, we're actually going to look at those internal forces right on this shear plane. And what we'll notice is rather than having shear stresses that are acting normal to the cut plane, they're actually going to act tangential, as your intuition would dictate. Okay. So, in the context, the design of bolted connections is actually a whole topic in and of itself. Today we're introducing it primarily to introduce the concept of shear stress, but as we go along, it's important to kind of talk about some of the particular vocabulary that you will run into as you design bolted connections. So often we will call P the total bearing force. Total bearing force, okay? And then the question is how do we really deal with this curved circular geometry, okay, when we're engineering bolted connections? So let's take a look at a close-up, a little bit more detailed drawing of the bolt geometry. So, as best as I can do here as I learn to use this tablet. It's not very good, but you get the point. Okay, now if we look at the kind of the image, if you were to, for example, project the image of this bolt as a shadow onto a wall, it would actually look like a plane, wouldn't it? Something like this. Okay, so this here would be kind of the projection of this bolt onto a plane. Okay, and so even though if you were to look at these resultant forces, these distributed forces, I should say, they're actually, in reality, they're kind of wrapping around the circular geometry in a very complicated way. Rather than actually capturing that circular area in order to calculate the stress, what we'll do instead is we'll just idealize the bolt to a plane. So we'll say instead, the cross-sectional area over which we're going to distribute the internal force is going to just be this plane. And so we'll call this A sub B. That's going to be the area of the rectangle. Okay. And again, we have this distributed load acting down this beam, and again, that is going to be our bearing force. Okay. And so what we'll say is this, if you take this bearing force in a bolted connection, like for example, this little close-up of the bolt perhaps is just this piece right here, okay? So if you look at this bolt, the way that we calculate what's called the bearing stress is simply F sub B over A sub B. Okay. Now notice that this actually isn't exactly right. This is what we would call an engineering idealization. Okay, we've made an engineering assumption that by picking this area here to simply be the rectangle, then that's close enough to the actual stress from a design perspective. Okay. Now let's kind of develop this a bit further, this idea of stress. Let's take a look at a different free body diagram. Okay. So let's draw our bolt that's in shear. Okay, we have our bolt. It's in shear. And instead of looking at those top and bottom portions where we introduce the idea of bearing stress, let's actually take a look at this middle section. Okay. This is as it was before. Okay, now what we want to do is let's pull this thing out here as a free body diagram. Okay, so we're going to pull that out as a free body diagram. And we're going to look at all the forces acting on that free body diagram. So the free body diagram is this part of the bolt here. Okay. And then we've got this distributed load acting on this side, which we will resolve into a resultant force. This is often what we do. Right? This resultant force is magnitude P. And then there are forces here. If we want to have a balance of forces, we have to figure out what forces are acting across the top of this bolt, right? Because there are forces over here that have to be accounted for in this free body diagram in order for us to have equilibrium. Okay? And so the resultant force coming from here we'll just call V equal to P over 2, acting like that. And then this one is likewise P over 2. Okay. And we'll call this a shear force, for example. Okay, let's see how it's shearing across the top of this bolt. And so in this case, again, going back to this idea of introducing vocabulary for bolted connections, we call a configuration like this, where you have a piece of a bolt where there's a shear force on the top and the bottom, we will call that double shear. And that shouldn't be a surprise. And so single shear would be, for example, if the only shear plane was this top one or this bottom one, but not both. And you can have triple shear. Any number of shear planes that develop in a bolted configuration, we just kind of call it, whatever you want to call it, single shear, double shear, triple shear. Okay. So this now brings us to what we need to introduce the idea of shear stress. And again, I want to kind of reiterate this concept that we're examining the idea of stress through particular applications. The first application was an axial bar in tension and compression, and that allowed us to kind of begin to understand an idea of normal stress for internal force over area. Now we're studying the application of bolted connections and introducing a little bit of design vocabulary there. But really what we're after is the configuration right here that will allow us now to introduce conceptually the idea of shear stress. So we're going to do that a few more times, and then about halfway through the course, or 2/3 of the way through the course, we will actually introduce the kind of the total concept of stress that incorporates all of these kind of snapshot views that we're taking of stress. Okay, so let's use the symbol tau, and in this case we'll just call it tau average. Okay, we'll call this thing shear stress, and we often use the symbol tau to denote a shear stress, whereas before, if you recall, we used sigma, another Greek letter, for normal stress. And the concept is very simple. It's still a kind of a resultant internal force, but this time it'll be the shear force distributed over the shear area. And so in this case up here, this shear force corresponds to this guy here, P over 2, and this area is going to correspond to the area over which we're going to distribute this load, right? And so the average stress up here actually would be the same as the average stress down here, because the area and the shear forces are the same. Okay. Now, let's, as we did for normal stress, let's introduce the idea of strain. So we'll introduce the concept of shear strain. Okay. And again, this, before when we talked about normal strain, it was very, very simple. It was delta over L, and your intuition really guides you to that perspective. But if you think about shear strain, what's happening with an object in shear, it's taking something like this little piece of material, subjecting it to, for example, some kind of shear forces like that, and you would anticipate that that little piece of material would be deformed into this parallelogram. Okay, so this is the kind of the geometry of shear strain. Is different than what we introduced for normal strain. And so this is an important part in mechanics, the development of the appropriate strain measure for the phenomena of interest. And so for studying shear, we need to understand how to measure this kind of deformation, right? There's not like a stretching or compression or going on. It's more like the object is just simply changing shape, but the area, for example, is staying the same. Okay, that's consistent with how we understand a shear strain. So to make this idea of shear strain a little more precise, let's go ahead and draw a little material element in its sheared configuration. It looks something like this. Okay. Now we know that the total angle between the two axes is pi over 2. And we're going to call this angle in here gamma over 2. And then we're going to call this angle in here, should be equal, gamma over 2. And then this angle in here, of course, must be pi over 2 minus gamma. Okay. All right, and so these angles, gamma, the symbol gamma is used to measure kind of the total distortion of the element, including both this upper distortion and this lower distortion, because the strain measure that you're using for shear has to somehow has to reflect the geometry of the deformation. And so this gamma, rather than being like, for example, an elongation, this actually here is a small angle. Okay. But we usually won't carry these units around. We'll say that this is also, in some sense, unitless as well. Okay. Now, we've got the idea of shear stress. We've introduced that. And then we've also introduced the idea of shear strain. Now, a fundamental thing in mechanics is shear stresses are a reflection of the internal forces. It's a way to kind of measure the internal forces that develop in an object. And the strain is a way to kind of measure the internal deformations. And so what you want to do is you want to connect them. So given some internal deformation state, what is the resulting shear forces? And so there is a Hooke's law, just like there was for normal stress. We'll call this Hooke's law for shear. Hooke's law for shear. Okay. And so the shear stress tau is equal to a measured quantity, G, times gamma. So you can see that this is very similar to what we did before. Remember, in normal stress, it was sigma equals E times epsilon. So this is what we did before, if you recall. Okay. So they have the same kind of mathematical signature, but they're measuring different phenomena. And we call G the shear modulus of elasticity. Okay, and this, of course, is the Young's modulus.